Okay, let's start today's session. Good afternoon, everyone. This is the sixth interactive session for NPTEL course Experimental Physics 2nd. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am a research scholar, Mrinalini from School of Physics, University of Hyderabad. And just for introduction, that these sessions we have every Saturday 3 to 5, where we discuss uh, numericals or some other theoretical concepts related to the five lectures or modules that professor covers every week. So yeah, you can ask your doubts or questions anytime in the during this session. Okay, let's have a recap of what we discussed last week, which was fifth week. So we had started by discussing the basic components of a spectrometer, where we are basically measuring the spectra of whatever the source is. It could be white light source or yellow light source like sodium light. So this is how a typical spectrometer looks, and we had discussed the basic components were the collimator, prism kept on the prism table, and this telescope through which we see the spectra, and then we do various studies or experiments. And the very important aspect that we start with is leveling of this whole setup that we do using the spirit level. We had discussed these things in detail. Also, we had discussed how to calculate the least count of the scale here, Vernier scale. Then we had discussed about prism. What is a prism? What it is made up of? What are different? How many sides it has? Which side is refractive? Which side is like we make it opaque so that we don't get any reflection from that side. And then depending on the refractive sides, like if incident light is incident on this side, then usually only these two sides are kept refracted, other are painted to be opaque or made to be opaque. So the angle between these two sides, as we had seen, is called angle of the prism. And then there is dispersion because of refractive index, which is phenomenon of the material. So it depends on wavelength of the light. So we know that white light consists of these 7 components constituting lights which have different wavelength. And then since refractive index of this material, which the prism is made up of, that will its refractive index will depend on wavelength. Means this we had seen that Cauchy relation also, that refractive index is given by something like this, typical for any general material. So it depends on the wavelength. Okay, so for like wavelength of red light is different, wavelength of violet light is different. So because of this, the bending or the dispersion when they pass through this glass or whatever material this is, prism, the bending or dispersion of these different wavelength of light is different, and that's why this spread of white light is seen into these 7 distinct lights. This is called dispersion. So this also we had derived, we had understood angle of prism, then uh, dispersion angle, which is like if there is no prism, then incident light will go straight, but if there is prism, then there is this angle of deviation, different for different wavelength. Of course, this is for red light, and then for violet light it is more. So we had understood this, and then we had derived the expression when angle of minimum deviation was another concept, that when the angle of incidence and angle of emergence, this is angle of emergence, when I make normal here, this will be angle of emergence, when they are equal. And when that happens, when the light passing through the prism is parallel to the base, so then that is the angle of minimum deviation. means the angle of incidence for which the angle of emergence is equal is known, gives us the angle of minimum deviation. And in that situation, so if I'll move this incidence angle less than that or more than that particular angle, then this dispersion will increase. Okay, so that is the particular angle at which the dispersion is the least, so we call it angle of minimum deviation. And we had seen the relation between them. I have not kept here, but we had seen the refractive index is related as this is angle of prism, this is minimum deviation, ratio of sine of a by 2. So this was the relation. Then we had found out other relations also with the refractive angles that we'll get inside. So, and yeah, based on them we had solved many numericals as well. So now yeah, this was also angle of prism, how we find out experimentally. This also was part of last week's, and the experiment, all of the experiments have been in detail explained in the lectures, so from there you can see. So after this one experiment, let's move on to this the experiments that were demonstrated this week. Again, here we will briefly discuss these experiments because in detail things are given. If you have any doubt, that you can ask here, otherwise we will mainly focus on numericals. So the second experiment that was part of last week was measurement of angle of minimum deviation of a given prism for particular wavelength. So here we are, of course, the refractive index is different for its function of wavelength, basically what we are seeing. So for different source of light, that means different wavelength of light, the refractive index is different. So here for a particular wavelength we are performing this experiment. So like in this particular demonstration, they had taken sodium vapor lamp source, and from this what basically we are doing here is we have collimator, prism and telescope, the basic three components of a spectrometer. So we will keep this prism in such a way that when we look from another side through telescope, as I said, we are looking for angle of minimum deviation. So if the angle that is being formed here, sorry, this is the normal to this first refracting surface, this is second refracting surface. Outside is air and this material is, let's say, glass. So this is angle of incidence, this is angle of emergence, and this angle of deviation is the deviation because of now we have kept the prism here, otherwise the light would be going in this direction. So this is angle of deviation, and if I'll increase this angle of incidence or decrease it, either I'll increase it or if I'll decrease it, okay, the deviation will increase, means this light that is coming out of the prism, it will move towards this side. For both the case, when I'll increase or decrease the incidence angle, but at this particular angle this deviation is minimum, that is this line going through the or traveling through the prism, it's parallel to the base. Only in this condition this R1 and R2 are equal, incidence angle, emergence angle are equal, and deviation is minimum. So we'll see this thing from the telescope that the light, when it's, for every case it will move towards this side, only at angle of minimum deviation it will be here. For every other angle it will start shifting towards this side. So when we reach this position, that position we have to note down, and after that we have to remove this prism and this direction of incidence light we have to note, and then difference between these two angles will give us how much is the minimum deviation. So this was what we had to basically do in this experiment. to find out angle of minimum deviation. This was one way to do this. The another experiment was determination of refractive index of material of given prism, again for one particular wavelength of light. So here what we had to do was, we will find out angle of prism that we had done in experiment 1 as shown here. Where is experiment? Yeah. So we had to measure angle of prism that we know from experiment 1 how to find out. Then from experiment 2 we know how to find out angle of minimum deviation. After finding out these two things, we have to just use this formula that we had derived last week, and using this formula we can find out the refractive index for that particular source of light. So this is pretty straightforward. The fourth one was, here what we had to do was, we wanted to this is experiment 4. What we wanted to do here was draw angle of incidence versus angle of deviation curve. So this is the plot that we wanted to get, again using a spectrometer, a prism, where by varying the angle of incidence, what is the deviation we are getting, that we were measuring in previous experiments. Now we wanted to plot those things. As you remember here, to find out angle of minimum deviation, we were changing the angle of incidence so that we can get this position where the deviation is minimum. But we were measuring only this particular position. We were taking reading only for this particular position to find out the angle of minimum deviation. But for now, the experiment that we are discussing, here we want to plot the deviation for all these angles that we are keeping rotating the prism to. So here, for some, as I said, even if I increase or decrease the incidence angle beyond or below this particular point, the deviation will always increase. As you can see, this is the particular incidence angle at which you can see on y-axis it is the minimum deviation we are getting here. If I increase incidence angle beyond this, then this deviation will increase. If I bring the incidence angle below this value also, the dispersion will increase. So when you will take the measurement by changing the incidence angle, we will see a plot like this, and the minimum value here will give us the angle of minimum deviation point. By when we make a tangent to this curve at the minima, then this point here, where is my cursor? Okay, this point here will give us angle of minimum deviation. Then further we had to calculate angle of prism using the formula and refractive index again. This fifth experiment was determination of calibration plot. Calibration plot is the plot between this dispersion, angle of dispersion, versus the wavelength. So as I said, refractive index depends on wavelength. For different wavelength of light, refractive index of the material will be different. Now refractive index is different, so dispersion is also different. So when we plot dispersion, this angle of deviation as function of wavelength, we get something like this graph. And here, actually this plot, this particular angle, deviation angle versus wavelength graph is called calibration graph. So this we had to plot first with this experiment, and then so further the second part of this experiment was, what is this? First part was, let me explain briefly what was the experiment. So in this experiment, first what we were doing, again we are taking our spectrometer, and the source first, we are keeping a sodium source. It is a yellow light source, and when we keep the source here somewhere, and from the collimator we are getting a particular wave, I mean this collimated sodium light. When it is incident, it refracts and it comes, and we will see it here through telescope. So here first step is we have to keep the prism in the minimum deviation position, so that the sodium light that we get on the other side is dispersed to the minimum. When we do this, after that, without disturbing the prism, we have to change this sodium source and replace it with some white light source, either mercury or helium light source, which gives white light, means it constitutes of these 7 wavelengths. So without this, as I said, without disturbing the prism, we have to remove this sodium source and keep the white light source, and then we have to measure the deviation for different wavelength. Here we had tried to keep the prism at angle of minimum deviation position, but for these, of course, now we are not changing the prism, so they won't be giving angle of minimum deviation, they will be just showing deviation, and that deviation with respect to those corresponding wavelength we will plot, then we will get a curve like this. So in this you can see maybe we had only 4 different wavelengths, so those 4 points we have plotted, and then we have connected all those data points which will be joined by a curve like this. Now what we see here, for corresponding to any particular wavelength, I can get the value of how much it will be deviated from this material. Like if the wavelength is say some point here, then I can take the extension from the y axis, and I can see the dispersion for or deviation for it will be this value. If I can do this, then I can do the opposite of it also, that if I know the deviation for that particular light, maybe I don't know what it is, its wavelength, but if I know how much is it's deviating, then I can find out corresponding wavelength. So all this that we were doing till now in these 2 steps was to get this plot, so that that's why we are calling it calibration plot, because once we get a calibration plot for a given prism and its position, then without disturbing the prism, again when we replace the source, and now we are using some unknown source, I don't know what is the wavelength, but when I'll take what is the deviation I am getting, and then I'll remove the prism and see where without deviation it's going, and this difference will give me deviation. Now I know the deviation, now I'll see corresponding to that deviation what is the corresponding wavelength value. So this is a way to know wavelength of unknown light source using this calibration plot. So in first part of this experiment we were calibrating the plot for that particular prism, and then in second part we are using that calibration plot to find out wavelength of unknown light source using this relation between angle of deviation and the wavelength. So this was the 5th experiment. Now there are other things that we need to understand related to these equipments. Okay, there is this refractive index versus wavelength curve, this experiment also. For that, let's understand so we have discussed many things in last week also. As I said, angle of prism, we discussed that between 2 refractive sides of a prism, the angle that is made between them, we call it angle of prism, and we usually denote it by capital A. Then we had seen some, this, as I said, angle of deviation, and then relation between them, as I discussed just few minutes back. Now there is something else we need to, one more, not phenomenon, but like another aspect of a prism, that is its dispersive power. A prism is also known by its dispersive power, and what do we mean by dispersive power of a prism? So when a white light enters a prism, glass prism, like as shown here in the diagram, we see another side, not the white light but these 7 different lights which we know this white light is made up of. But why is it splitting when it's coming out of this? That, as we had discussed earlier also, is because of refractive index, which is varying for these different wavelengths. The refractive index is different for these wavelengths. Because of this, the angle of dispersion is different corresponding to different wavelengths. Because of this, the white light is breaking into its constituent colors, and this phenomenon is called dispersion. This spectrum is collection of different colors, 7 colors that we know, and the separation of white light into these constituent colors through this glass prism is known as, the phenomenon is known as dispersion, and the separation is, how much it can separate is the dispersive power of this glass medium or the prism that we are talking about. Okay, so yeah, let's now see let's try to derive actually what is the how do we calculate, what is the formula for finding out the dispersion or dispersive power of a prism. So here, if we see, this is what I am saying, that because refractive index is different for different, this is red, yellow, violet, we have just taken 3 here, in between others are there. So because the wavelength is different, refractive index is different, and the dispersion that these wavelengths encounter is different. If you remember, last week we had started with we had derived refractive index, which was depending on angle of prism and angle of minimum deviation in this way. This was the refractive index of the glass prism. This is angle of prism, and this is the angle of minimum deviation for that particular wavelength. So this is the refractive index for a particular wavelength of that particular glass prism that we are talking about. Now here you will be seeing, we are talking about glass prism, which is a thin glass prism. Or what do we mean by thin glass prism is, this refractive angle A is not too much, like it's a small angle. It is small enough that we can we can approximate sine of A by 2 to A by 2. Okay, how this happens is, sine theta, when we write it as, when we expand it, we get it as theta minus theta cube by 3 factorial, theta phi by 5 factorial, and so on. Right? This is how sine theta expansion is, Taylor series expansion or something. So when this theta is very small, then these terms are not very significant. In that case, we can just approximate sine theta to theta. So using the same approximation, here what I am saying is, the angle of prism is small enough that I can assume sine of A by 2 to A by 2. Okay, and similarly sine of A plus delta m by 2 to, I'll approximate this also to A plus delta m by 2. When this happens, what we get is, refractive index will become A plus delta m by 2 divided by A by 2. Now this denominator 2 will be cancelled, and we will get A plus delta m by A. Taking this denominator to left, we will get refractive index multiplied by angle of prism is equal to A plus delta m. Now from this, delta m will be mu A minus A, which will be mu minus 1 when I will take common the angle of prism. Okay, so the relation between the angle of minimum deviation, refractive index, and angle of prism, we get something like this. So this is the angle of minimum deviation formula for particular refractive index of a prism which has angle of prism is A. So this is one formula. From this what we can see is the angular dispersion. So what do we mean by angular dispersion? As we were explaining, when white light splits into constituent lights, that is known as dispersion. One light is encountering minimum deviation. As we can see, red light is bending less, means its deviation is less, because the original light is going somewhere here. So the deviation is less for red light, the deviation is more for this last violet light, and others are in between. So this deviation from original path is happening for all the 7 lights, but it is covering a range. The deviation starts, say for this delta R, and this is delta V. So deviation starts from delta R, then it goes on to delta V. This range, this angular range is what we call angular dispersion. The dispersion is happening and it's covering a particular angular range. That is, dispersion is covering this angular range. So this range is called angular dispersion. So what I am here saying that for particular refractive index, which depends on, which will be different for red light, which will be different for violet light, we will get angle of minimum deviation. So angular dispersion, if I write it in formula, angular dispersion will be equal to the deviation. So deviation is maximum for violet light, deviation is minimum for red light, and I am talking about again this angular range I am talking about. So this is dispersion for violet light and deviation for violet light, deviation for red light, because this value is higher, so I am subtracting deviation of red light from the deviation of violet light, because this value is bigger than this. Okay, so this will give me the angular dispersion of the white light that is incident on this prism. I hope you understood what I am trying to say. So this was like what we are understanding. To put it in mathematical form, it will come like this. So this, in terms of refractive index, will become from this formula that we have just derived. So delta V means mu V minus 1. Angle of prism will be same, it doesn't depend on wavelength, it doesn't depend on anything, it is just constant for a particular material, minus mu R minus 1, okay, mu VA minus A minus mu RA, okay, let me keep it like this, mu RA minus A. This will be mu V times A minus mu R times A plus A. So this will be cancelled and we will be left with mu V A minus mu RA. If I take out A common, then it will be mu V minus mu R times A. So angular dispersion, either I can write it as this, or in terms of refractive index, angular dispersion the formula is, in terms of refractive index and angle of prism, can be written like this. Okay. Now, as you can see here, we know the white light splits into Vibgyor, this violet, indigo, blue, green, yellow, orange, red. So yellow is actually considered the intermediate, the middle kind of wavelength, and when we consider it, whatever values we get, it comes out to be close. So we can take it like this, and usually it is taken like this, that yellow light is considered the to have the middle value in this particular spectra. So for yellow light, let me have slide. right now we have got the formula for angular dispersion. Now next we need to find out dispersive power formula for the prism material. Take one more slide, I think is sufficient. So this was angular dispersion relation. Now this angle of minimum deviation relation for yellow light will be, okay, sorry, yeah. So this thing for yellow light will be refractive index for yellow light minus 1 times angle of prism, which is constant. Okay, now so this is the left hand side. Let me write what I mean here is, here I got this is the left hand side part, right hand side we get so taking this as equation 1, and this is the relation for yellow light. And this was the angular dispersion that we covered between red and violet. And this particular is for yellow light. Taking this as equation 2, when we divide equation 1 by equation 2, we get on the left hand side will be delta V minus delta R divided by delta Y is equal to, on the right hand side we will get mu V minus mu R times A. Denominator will be mu Y minus 1 times A. This will be cancelled, and this is the ratio which is known as dispersive power of material of prism. So this delta V minus delta R was angular dispersion, and when we divide that by deviation of the mean wavelength, which is yellow, we consider is the mean wavelength between violet and red, and when we take ratio of these angular dispersions, then we get dispersive power of the material of the prism. So to we denote dispersive power by omega, and the SI unit of this dispersive power that we measure is in watts. Okay, so this ratio of angular dispersion for any two wavelengths of light to the deviation of mean wavelength, which is yellow, so this mean wavelength, this ratio is known as dispersive power of the material of prism. So this is how we define dispersive power of material of prism, and this is the relation. And okay, so there is, after this, so we have discussed angular dispersion, we have discussed dispersive power of material of prism. Now the resolving power, we don't need to derive it. This was also just, we can, for knowledge, we can just take it that the formula is, actually it's the wavelength versus difference in wavelength, and the formula is given by d lambda. So this is also, you can keep in mind, resolving power is given like this. Okay, now let's start discussing the questions that we have based on this week's topic, this week's concepts actually that we had discussed. So the first question is, Yeah, so just to tell you guys that these questions that I've taken is from 2024, that is last year's the same course when was done, whatever were the assignment questions that time, those I'm solving it for you because I cannot solve your assignment questions that is due in few days, but these are the similar questions from the same week last year, so I think these will be useful. Apart from this, still if you have doubt you can ask related to this week's concepts. Okay, so first question is the essential parts of a spectrometer are. So, as we have discussed many times, essential parts of a spectrometer: the collimator, behind which we keep our light source, and then we adjust the slit of the collimator so that we get parallel light and very narrow beam, so that we can consider this collimator as source for our prism. And then we have prism, and then we have telescope or eyepiece through which we see or measure these lights that are passing through the prism. So this collimator, prism and telescope are the main components of a spectrometer. So prism table and prism, uh, yeah, they are, but we need collimator and telescope also. Collimator, telescope and prism table are the essential parts of a spectrometer. So this C is the correct option. The second question is mainly what type of spectra are obtained. So maybe this aspect has not been discussed in the lectures. I think for in coming week it could be covered, but right now for your basic understanding, I want to explain that there are actually two types of spectra that we obtain. These are absorption spectra and emission spectra. These are the two types of spectra that we observe, that we see, that we use to do any experiment. So the correct answer is here emission spectra and absorption spectra. Now just to tell little theory about these things, that how we get emission spectra and how do we get absorption spectra. So if we have some atom, okay, some sample which has some sort of material, and material will have some atom, when that material, the atom of that particular material will absorb some energy from, we know at the center we have nucleus, and then we have different energy levels. So when the energy is absorbed by inner shell, this is the lowest energy level, this is higher than this is even higher. So as we go towards outer shells, the energy of the atoms in that shell is also increasing. So when this energy is absorbed by this inner shell electron, or inner shell electron, then it absorbs that and goes to higher energy level. When it does that, then this light gets absorbed, we will not see anything here. Okay, so if my source was, say, some white light, for example, say it was white light, and on another side of the spectrometer I'll be getting this spectrometer I'm using, so of course they will split into the respective Vibgyor series, and I'll be seeing red to violet lights like this. But if I put a sample in between such that it absorbs some, which it will absorb again because discrete, it has the energy difference is discrete here, so it will absorb depending on the what kind of material it is, because the difference in energy levels also depends on the type of material. So depending on the type of material, which part of this whole spectra it will absorb, it depends on the material. So whichever part of the spectra it will absorb, then it will go to excited energy. That part will be missing from what I'll see on the other side. If this sample is not kept, again I'm repeating, then I'll be seeing this spectra on the other side, because there is prism in between and it's getting dispersion is happening. But if I keep a sample in between, then because of this particular thing that I explained, the electron of that atom of that sample will absorb some particular wavelength which is equal to the energy difference here and go to excited level. So that particular wavelength will be missing. Okay. Then the spectra that we get is known as absorption spectra. And on the contrary, if I have some material where due to some reason, I don't know how, I mean we don't bother how the electrons have reached high energy level, but when they come down, because when they are at high energy level, that is unstable state. Okay, so somehow we made the electrons to go to high energy level, but since that is unstable state, now they'll try to come down. When they'll come down to the lower energy level, the differential amount of energy will be given out in form of some wavelength, some radiative wavelength, and that we'll see as some light spectra. So otherwise it should be whole black, but since it's giving out, the particular sample is giving out the light at those particular wavelengths, that wavelength will be corresponding to the energy difference of the higher energy level and lower energy level of these atoms. So those particular wavelengths we will be able to see. So this is the difference between absorption and emission spectra, and these are the two typical types of spectra that we see and use. So just to define once again, what is absorption spectrum? An absorption spectrum is constituted by frequencies of light transmitted with dark bands when energy is absorbed by electrons in the ground state to reach higher energy states, which is this. So we get dark bands because it's absorbing the energy. Whereas for emission spectrum, what is happening? When energy is absorbed by electrons of atom, electrons move from lower energy to higher energy levels. So this part we don't know how it's happening, but for our case, we just start that it is at higher level. We don't know how, but we start that electron is at higher level, and now from there, when excited electrons have to radiate energy to return to ground state, then they'll emit some wavelength, some radiation, which we'll see, and this is known as emission spectra. So these are these two types of spectra. The difference, if we talk about the difference between them, so emission spectra happens when atoms release energy, whereas absorption spectra happens when they absorb energy and go to higher level. Emission spectra comprises of colored lines. We get particular lines in the dark band, whereas absorption spectra gives us dark lines on colored background. For emission spectra, so they have their applications. These things we can further, maybe are there in further experiments where we can discuss in detail, but just to mention it, emission spectra is helpful in figuring out composition of certain matter. So as I was telling that which particular wavelength light the atom or that sample will be absorbed depends on the sample. Why? Because the energy difference between different shells is different for different material. So this depending on which wavelength or which particular radiation we are seeing, we can find out, we can say what kind of material that is. Can be used to figure out the ability of certain objects to retain heat and absorption level. This is the application of absorption spectra usually. So the type of photon emitted is helpful in figuring out kind of element the substance is made up of. This is again same thing. An element radiates a different amount of energy and has a unique emission level, because of course we know the energy level depends on n and z square, so it depends on the atomic number of this element. Okay, so the correct answer for this question was the different types of spectra. The important characterization, actually categorization, I mean important categorization is emission spectra and absorption spectra. Third question is, what is the condition for obtaining minimum deviation? Just to recall, when we have a prism like this is refracting surface 1. Just let me write one. Let's call this A, B, C. What is happening? C. This is B. Okay. This is one refracting surface, AB. Another refracting surface is AC. When I'll draw normal to this and normal to this, if this is the angle of incidence, I've explained this earlier also, just for this question again. And this is the angle of emergence. This is refractive angle 1, this is refractive angle 2. So when this line passing through the prism becomes parallel to the base of the prism, which is BC, in that particular condition, so when this ray of light becomes parallel to the base of prism, that time we say that the incidence and this incident light will be deviated minimum. The deviation will be minimum. And what happens in this angle of minimum deviation position is that angle of incidence is equal to angle of emergence. Also, refractive angle 1 is equal to refractive angle 2. So what is the condition for obtaining minimum deviation? Deviation of ray, what is wrong here? Deviation of ray would be minimal when angle of incidence is greater than angle of emergence. No, this does not happen in minimum deviation condition. Deviation of ray would be minimum when angle of incidence is smaller than angle of emergence. No, this is also does not happen for angle of minimum deviation position. Deviation of ray would be minimum when refractive angle of prism is 90 degree. No such requirement as there. Deviation of ray would be minimum when angle of incidence and angle of emergence are equal. And this is how, if you remember, in the experiment 2 we were discussing that we were seeing in experiment 2 we were seeing this is how we were finding out angle of minimum deviation. By collimator, the ray is incident on the prism. On another side, using this telescope or eyepiece, we are trying to see the position of the prism where the deviation is minimum. So, and at that position, the incidence angle and emergence angle becomes equal, as I told you now as well. So the correct answer is deviation of ray would be minimum when angle of incidence and angle of emergence are equal. D is the correct option. Now fourth question, how does the deviation change with the color of incident light for a thin prism? Again, we had done the whole derivation using thin prism approximation. Okay, so how does the deviation change with the color of incident light? So this, I told you that refractive index, and we saw that refractive index depends on wavelength of the material. Now let's see, refractive index we define as ratio of speed of light in air, which we denote by c, and speed of light in the medium, let's denote by V. So this is speed of light in air or vacuum, which is almost same. Then speed of light in medium. This is how we define refractive index of this medium. We are talking about this medium. Then we know that velocity of any light is given by frequency times its wavelength. Now putting this relation here, refractive index will be this will be nu times lambda. Frequency we know does not depend on the medium, it is the property or characteristic of the source. So this will anyway won't change. What will change is the wavelength. So this lambda is the wavelength for this medium, not in air, in this particular medium. When we put those things here, we can clearly see refractive index depends on wavelength, something like this. Okay, so if wavelength of that light is more, refractive index for it will be less. We know refractive index for red light is more than refractive index, wavelength of red light is more than wavelength of violet light. From this relation, that means the refractive index of red light will be less than refractive index of violet light, because they are inversely proportional. So what here we were talking about, deviation change with color of incident light. Deviation is greater for red light than for violet light, and this deviation also, because refractive index, we had seen the relation, right, between refractive index and deviation. We had derived it here. Yeah. So from this we can see that deviation is kind of proportional to refractive index. And in this particular question they are talking about deviation, that how much it's bending. And since I just showed you that deviation depends on refractive index, so higher the refractive index, more is the deviation. And wavelength, and the relation between wavelength and refractive index is they are inversely related. So red light wavelength is more, so its refractive index will be less, and since refractive index is less, that means the deviation for red light will be less than the deviation for violet light. And that is why we see, whenever we put our prism, we see always red light first, and or red light on the top and violet light at the bottom, because the bending of red light is less and the bending of violet light is more. Okay, and that's why there are many other phenomena also because of this refraction, right? That in the morning and sunrise and sunset time we see red light, more orangish reddish sky, whereas the noon time we see violet color or blue color of the sky. All these things, natural things that we see around us, comes because of all this dispersion, refraction happening in the nature. Okay, so the correct answer here was deviation is greater for violet light than for red light. Deviation is more for violet light and less for red light. So B is the correct option here. Next question. Yeah. So this I have just shown that deviation for red light is less and deviation for blue light is, or blue or violet light, they all come at the end, is more. In the question they were talking about violet light. So yeah, violet light. Because the wavelength is more, refractive index is less, and that's why the deviation is also less. Blue or violet, whatever the question says. And this dispersive property of material, the dispersive property of material, as we see, it depends on the wavelength. Okay, so for different wavelengths, this dispersive or deviation is different. Next question, the fifth question: why sodium light is not considered strictly a monochromatic light? Okay, so again, if we'll be studying about further, maybe in coming weeks, if we'll be discussing in detail about these absorption and emission spectra, that time we'll discuss. So right now, like I gave you hint that around the nucleus, as we have different energy levels, and when electron go from lower energy level to higher energy level, or comes from higher energy level to lower energy level, in that situation we get some spectra. And this energy level, when we study further, we get to know it's not only given by n is equal to 1 or n is equal to 2. Because of something, there are more couplings, something known as spin orbit coupling. If you recall, we give our principal quantum number, we call n. Then we call magnetic quantum number or azimuthal quantum number m. If this is 2, then m becomes -2, -1, 0, 1, 2. And then spin quantum number also comes +12, -12. So there are different these quantum numbers which help us determine the energy level. So it's not only this n is equal to 1 is k, this n or this n is equal to 2l. There are sub levels, sub energy levels here, depending on j that we calculate. So I mean, there are finer sub levels corresponding to this particular L, M, N shells, and because of these this splitting of the energy level, we don't always get one absorption wavelength or one emission wavelength. So the same thing happens for sodium light, which we see as yellow, but when actually it was explored, it was observed that very two close lines are there, which when we resolve, we use a good resolution telescope, then we are able to see that they have two yellow, we call it D1 and D2 sodium light, sodium wavelengths. One is 5890 angstrom, another is 5896 angstrom. So why sodium light is not considered strictly a monochromatic? Because it is constituted of D1, D2 lights, which already has been discovered. So we know that it is not monochromatic source, and sodium light contains two wavelengths. And why it happens is this diagram I am showing. So the 3p level has, as I said, this is J value, which is 3 by 2 and half. So because of this, the energy level that we think is single actually is very close but splitted into these two levels. And when it comes to this 3s level, electron can come from 3p to 3s and 3p half to 3s. Because of this, we will get very close values of wavelength, which only after using a very high resolution telescope we will be able to resolve and see that they are actually two different, 5890 angstrom, 5896 angstrom. The difference is of around 6 angstrom between them. And then if we don't use that high resolution telescope, then we will just see single yellow emission spectra. But if we will use this high resolution telescope, we will see that there is 6 angstrom difference between these two, and D1 and D2 sodium vapor source wavelength. And this happens because of the spin orbit coupling, the coupling between spin and orbital angular momentum, which gives us total angular momentum, this 3/2 and half. So this may be, if it's required, we can discuss in detail later. Like for this, here the correct answer is C. So because it's constituted of these two wavelengths, we don't consider strictly the sodium source to be monochromatic. Okay, so the sixth question is, why is it necessary to level the spectrometer? So this we had discussed last time. Why is it important to level the spectrometer setup, and we use spirit level to do it? Because if it's not leveled, there are many sources of and many chances of us taking the wrong reading, because we'll be getting, it's not just to get bright image, and to obtain multiple, we don't want multiple image of slit. Leveling is necessary, otherwise the position of image will be different for different position of telescope. And we know if leveling is correct, we'll get only for particular incidence angle, the telescope position would be the same if we want to get the brightest refracted or emergent light. That will happen only at the same position. Like if this angle I'm keeping here and my incident light is coming like this and emergent is coming in this direction, say, then if my telescope is kept here, then I would see not the brightest light, I'll see a little dull. When it's here again, I'll see dull. So when I'll keep exactly in front of this emergent light, then I'll see the maximum intensity of this light, and I'll get to know this is the correct direction of the emergent light, and then I can take the angle reading from the vernier scale. But if the level is not correct, level of the collimator, level of the prism table, and level of the telescope, they are not at the same horizontal level, then this telescope position will not be unique, and that will be a big problem when we are trying to take the reading of the positions. So this is the reason why leveling is important. Seventh question is, the deviation produced by a flint glass prism for violet and red light rays are 3.25 degree and 3.10 degree. So flint glass prism, this is the material of the prism, and the deviation for violet and red light has been given. So deviation for violet light is 3.25 degrees, and deviation for red light is given to be 3.10 degrees respectively. Yeah. Find the angular dispersion. So we have to find out angular dispersion. Now recall the derivation we had done, that white light incident on a prism, it splits into seven of its components because of the deviation, right? Actually it bends, and this angular range it starts bending one light at this particular angle and other lights to a higher and higher angle, and the angular range it covers is what we were calling angular dispersion. So we will get the angular dispersion by delta V minus delta R. Why we are taking this deviation in V first? Because it's a higher value. As you can see, V violet light, which has smaller wavelength, bends more or deviates more. So we are taking deviation of it first, and deviation of it is 3.25 angstrom, degree minus 3.10 degree, and the difference will be 3.25 minus 3.10. So the angular dispersion is 0.15 degree. So the correct answer here is A. 0.15 degree is the angular dispersion. Now the next question, question number 8. The refractive index of crown glass is 1.685 for violet light. We know refractive index depends on wavelength. So here they are saying that for violet light, we don't know its wavelength, but I'm just denoting it like this. This is the wavelength for violet light. For violet light, or let me write here, for violet light, refractive index of some crown glass material is 1.685, and refractive index you know is a ratio, so it's unitless. For red light, the refractive index of the material is 1.644, right? Refractive index of crown glass is 1.685 for violet light and 1.644 for red light. Find the angular dispersion produced by prism of angle 4 degree. We have to find out angular dispersion. Okay, and the angle of prism is given. So one relation we know, right here, that angular dispersion is given by this angular spread, right, that we just talked in previous question. Now here we have not been given the deviation in angle. We have been given the refractive index, and that relation also we had obtained. If, yeah, here this is angular dispersion, and the same thing in terms of refractive index of these materials will be given by this relation. So using this formula that we had derived in advance, we can directly use it here. So this is equal to refractive index of violet light minus refractive index of red light multiplied by angle of the prism. Now prism angle we have been given, which is 4 degree. So substituting the values here, refractive index of violet light is 1.685 minus 1.644 multiplied by 4 degree. All this thing is in degree. This was this is in degree and this is unitless. So answer will be in degree. Now let me do this using calculator. We'll do 1.685 minus 1.644. This will give us 0.041 multiplied by 4 degrees, which is the angle of the prism. So multiplying by 4, we'll get 0.164 degrees. This is the angular dispersion, 0.164. C is the correct answer. So in previous question we had done it by knowing the angle of deviation, but here even if we don't know angle of deviation, just if we know the refractive index for those particular wavelengths, we can find out the angular dispersion using this formula. We just need to know the angle of the prism as well. Okay, so the next question, question number 9. The deviations produced for violet, yellow and red lights in the case of crown glass prism, some prism again we have, okay, and the deviation is what we have been given. So deviation for violet light is 3.72 degree, deviation for yellow light is 3.28 degrees, and deviation for red light is 2.84 degrees. Because it's been given that deviation produced for violet, yellow and red light for this prism is 3.72, 3.28 and 2.84 degree respectively. So just like we have to follow the order. Violet, yellow and red light have corresponding 3.72 degree, 3.28 degree and 2.84 degrees of deviation. As you can see here, deviation is minimum for red light, deviation is maximum for violet light. Why? Because wavelength is higher for red light and wavelength is less for violet light, and refractive index changes according to wavelength, and that's why the deviation also changes. Okay, so the question is, calculate the dispersive power of the prism. So here we have to not just only calculate angular dispersion but dispersive power of the prism. Now this also we had derived earlier. We had derived dispersive power formula, and yeah, sorry, this was the angular dispersion in terms of refractive index it was, and from this we had defined the dispersive power of a prism material as the ratio of deviation of these two wavelengths to the ratio of deviation of the intermediate wavelength that we are considering. Usually we always considered yellow light. So when we take this ratio, we get our dispersive power of the material. So using that formula here, yeah, we'll use that formula here. So dispersive power of the prism will be deviation in violet light, deviation in red light to the ratio of deviation in yellow light. And all these three things we have been given. We'll substitute the values. Delta V is 3.72 degrees minus 2.84 degrees deviation for red light, and then denominator we have deviation for yellow light, which is 3.28 degrees. 3.28 degrees. So the numerator will become 3.72 minus 2.84 is 0.88 degrees divided by 3.828 degrees. It will be divided by 3.28. This will give 0.26829. Like in calculator it will keep on giving, but we have to see, we have to consider three significant figures. So we'll keep it to up to 3 decimal digits, 0.268. Right, if we'll round it off it will be 3, and if we'll round 3 it will be just 0.268 degrees. So the correct answer will be this option B, 0.268 degrees. Sorry, won't be in degree. 0.268 will be the dispersive power of the prism, because this is the ratio of these. Okay, now next question is, if the refractive index for red and violet colors for some prism material are given as 1.5155 and 1.5245 respectively. So refractive index is given for red light, the value is 1.5155, and refractive index for violet color is given as 1.5245 respectively. Find the dispersive power for this prism material. Now here we have used deviation dependence formula for dispersive power calculation. Now for calculating dispersive power in this particular situation, we'll use the relation depending on refractive index. Now here we had derived that as well. Yeah, here you can see this was dispersive power in terms of angle of deviation. Somebody's mic is unmuted. Okay. So this was in terms of this deviation and then we had also found it in terms of refractive index. So this is the formula of dispersive power in terms of refractive index. So we'll use this formula for this particular question, and the formula is refractive index of violet light minus refractive index of red light divided by refractive index of yellow light minus 1. Using this and substituting the values here. Okay, so one thing is missing here in the the things that we have been given in this question is, you can see we have refractive index for violet light, we have refractive index for red light, but we don't have refractive index given for yellow light. So as I said, we consider yellow light to be the mean wavelength, like it is the intermediate between red, which is higher wavelength, violet, which is the least wavelength in component of white light I'm talking about. So white light splits and gives this all 7. Red has highest wavelength among that and violet has least wavelength. Yellow we consider is intermediate between them. So to find out the refractive index of yellow light, we just take average of these two refractive index. This is what should be done. Refractive index for yellow light will be average of refractive index for violet light and refractive index of red light. We just take average of this. Okay, so let's calculate this. The value of violet light is 1.5245 plus refractive index for red light is 1.5155. So they have given us accuracy to 4th decimal digit. So our answer also we'll keep like that. This will be 1.5245 plus 1.5155 divided by 2. This will be 1.52. This will be refractive index. That means it is like this. 1.5200 is the refractive index for yellow light. So we will substitute all these three values here. Refractive index of violet light is 1.5245 minus refractive index of red light is 1.5155 divided by refractive index of yellow light, which is 1.5200 minus 1. 1.5245 minus 1.5155 will give 0.009, and in the denominator it will be 0.5200. When we will do this division, we obtain 0.009 divided by 0.52. Answer is 0.0173. The C option. Okay, this is C option is the correct answer here. So the dispersive power for crown glass prism here, not using the deviation angle but using the refractive index, the formula is this. And how to find out the yellow light, the refractive index for yellow light, is by taking average of the refractive indices for violet and red light, because we consider yellow light to be in between these two. So this we have obtained, and yeah, so these were the questions that were given as assignment problems last year for this same week, and I hope using these you will be able to solve your assignment problems of this week. If you have any particular question, you can let me know. Either I'll be able to help now or maybe we can discuss later. So yeah, these were the, so till now we have been discussing several experiments based on using spectrometer only actually. From next week I think we will be discussing more of interference where we use gratings. That also we'll discuss what is the principle behind it. So till now we were discussing spectrometer based experiments using prism, and then we try to understand different parts of prism, its angle, angle of deviation, angle of minimum deviation, how to find out angle of prism or how to measure angle of minimum deviation, then how to get this calibration graph so that we can get to know wavelength of any light using, if we calibrate and we have this calibration plot for particular position of prism in a spectrometer, then we can use any unknown source, and when we whatever angle of deviation we'll measure from this calibration plot, corresponding wavelength we can find out. So these were the basic experiments that were discussed this week. And then so this was one more experiment. It was on, we had to draw refractive index versus wavelength curve in this particular experiment. Again, here we are using a spectrometer, and this refractive index versus wavelength curve is called dispersive curve actually. And there were several steps. Details, you please watch the video. And when we plot this graph further, we had to find out dispersive power, again the formulas that we have discussed, using them. And using the same experiment further, we had to verify Cauchy's relation and plot graph between, this is resolution power versus wavelength, and then also find out resolution power from this particular experiment. So this is like, you can do the experiment and find out these things, or if you know the parameters given, then numerically you can find out the things as we discussed later. So these were the 6 experiments till now that have been discussed using spectrometer and prism. And we have also discussed today dispersion phenomenon, and because of that, what do we mean by angular dispersion, and dispersive power of prism material, how to get the formula using this small derivation, and how the material's refractive index depend on the wavelength. So yeah, these were the questions that I found were relevant for this week. If you guys have any question, otherwise we'll be ending this session here. So if you guys have doubt, you can ask, or is everything clear? Okay, thank you, Vijay Lakshmi. Yeah, if everything is clear, then fine. Do you have any questions?
Yes, ma'am. No, ma'am. No, ma'am.
Okay, okay. Then I'll stop the recording.